Welcome! In this session, we'll explore LeetCode problem number 2065, maximum path quality of a graph. This problem challenges us to maximize the quality of a path in a graph while adhering to certain constraints. Let's dive in and break down the solution step by step. The problem involves an undirected graph with n nodes labeled from 0 to n1. Each node has a value associated with it, represented by the array values, where the value at index I corresponds to the value of node I. Additionally, the graph is defined by an array of edges, where each edge specifies two connected nodes, along with the time it takes to traverse that edge. For example, an edge, u, v, time, means there is an undirected connection between nodes u and v that takes time seconds to travel. You are also given a maximum time limit, max time, which represents the total time you can spend traversing the graph. The goal is to determine the maximum path quality achievable within this time constraint, starting and ending at node 0. Path quality is calculated as the sum of the values of the unique nodes visited during the path. While nodes can be revisited, their values contribute to the path quality only the first time they are visited. To summarize, the task is to find the optimal route that starts and ends at node 0, respects the time limit, and maximizes path quality. The input format includes three key components. First, the array values, which is an integer array of size n. Each entry in this array represents the value of the corresponding node. Second, the edges array, which is a two-dimensional list where each subarray specifies a connection between nodes u and v and the traversal time for that edge. Finally, an integer max time is given, which defines the upper limit on the total time that can be spent traversing the graph. The output format is a single integer, the maximum path quality obtainable under these constraints. Let's consider some examples to better understand this problem. In the first example, the graph is defined by values equals 0, 32, 10, 43, edges equals 0, 1, 10, 1, 2, 15, 0, 3, 10, and max time equals 49. The output for this input is 75. This represents the highest path quality achievable while adhering to the rules. We'll break this down step by step. In the first example, one valid path is 0-1-0-3-0. The total time spent on this path is calculated as 10 for each edge traversed, 10 plus 10 plus 10 plus 10, which equals 40 seconds. Since 40 is less than or equal to the maximum allowed time of 49 seconds, this path is valid. The unique nodes visited along this path are nodes 0, 1, and 3. To calculate the path quality, we sum up the values of these unique nodes, values 0 plus values 1 plus values 3, which equals 0 plus 32 plus 43, resulting in a path quality of 75. Importantly, no other valid paths in this graph offer a higher path quality, which is why the output for this example is 75. This example illustrates how the constraints work and how we calculate both path quality and traversal time. In the second example, the graph is defined by values equals 5, 10, 15, 20, edges equals 0, 1, 10, 1, 2, 10, 0, 3, 10, and max time equals 30. The output for this example is 25. Let's examine why. A possible path, 0-1-0-3-0, has a traversal time of 10 plus 10 plus 10 plus 10, which equals 40 seconds. This exceeds the maximum time allowed, making the path invalid. However, another valid path is 0-3-0. The time spent on this path is 10 seconds for each edge, resulting in a total of 20 seconds, which is within the allowed time limit. For this path, the unique nodes visited are nodes 0 and 3. The path quality is calculated as values 0 plus values 3, which equals 5 plus 20, resulting in a value of 25. Since no other valid paths offer a higher path quality, the output for this example is 25. In the third example, the graph is defined by values equals 1, 2, 3, 4, edges equals 0, 1, 10, 1, 2, 10, 2, 3, 10, 0, 2, 15, and max time equals 25. The output for this example is 7. The only valid path is 0-1-0. The total time spent on this path is 10 seconds for each edge traversed, adding up to 20 seconds, which is within the time limit. The unique nodes visited are nodes 0 and 1. The path quality is calculated as values 0 plus values 1, which equals 1 plus 2, resulting in a value of 3. Another possible path, 0-2-0, has a traversal time of 15 plus 15, which equals 30 seconds. This exceeds the time limit, making it invalid. Since no other valid paths with a higher path quality exist, the output for this example is 7. Several edge cases should be considered for this problem. First, in the case of a single-node graph where n equals 1, the only valid path is the node itself, and the result is simply values 0. Second, if there are disconnected nodes in the graph that are unreachable from node 0, their values cannot contribute to the path quality, as they cannot be visited. Third, if max time is smaller than the smallest edge time, the only valid path is staying at node 0, since no edges can be traversed. Fourth, in graphs with cycles, care must be taken to ensure that paths with cycles are considered valid and that their traversal times are accurately accounted for. Finally, if there are multiple paths with the same maximum path quality, any of these paths can be considered valid, as the problem only requires the highest path quality, not the specific path itself. To solve the maximum path quality of a graph problem, the goal is to maximize the path quality while adhering to the constraints given. Since this is a graph traversal problem, we start by exploring different approaches. One option is the brute force approach, where we systematically explore all possible paths originating from node 0. Using depth-first search, we would calculate the path quality for each route while keeping track of visited nodes, and backtracking is needed to explore alternate paths. However, this approach is computationally expensive. The time complexity grows exponentially, as we would need to examine every possible path, making it infeasible for larger graphs. Additionally, the space complexity is linear due to the recursion stack used during the DFS traversal. The major drawback of the brute force approach is its inefficiency. The exponential time complexity means it quickly becomes impractical as the graph scales, and redundant calculations further exacerbate the problem. To address these limitations, an optimized DFS approach with pruning can be applied. Here, we still use DFS but incorporate strategies to skip unnecessary paths. By leveraging the time constraint, we can terminate paths that exceed the allowed time and avoid wasting computational resources. Additionally, by maintaining a frequency count of node visits, we can calculate path quality more efficiently. Memoization is another key technique in this approach, allowing us to cache results for specific states, such as the current node and remaining time, so we don't recompute values for states we've already explored. These optimizations dramatically reduce the time complexity to a manageable O, n*e, where n is the number of nodes and e is the number of edges. The optimized DFS approach with pruning offers significant benefits. By avoiding redundant calculations and eliminating unnecessary searches, it is much more efficient than brute force, especially for larger graphs. Another alternative to consider is a dynamic programming-based approach. With this strategy, we define a state dp, node, time, to represent the maximum path quality achievable at a specific node with a given amount of time remaining. Transitions between states are determined by the graph structure and the time constraints, and the solution is computed using a bottom-up approach. This method avoids recomputation, which ensures that the results are optimal. The time complexity of this approach is O, n*t, where t is the maximum time allowed, and the space complexity is also O, n*t, due to the storage requirements of the DP table. The dynamic programming approach, while efficient in theory, has its own drawbacks. One major limitation is its memory usage. The space complexity can be prohibitive for large time constraints, as the DP table grows with the product of the number of nodes and the maximum time. Additionally, implementing this approach is more complex compared to DFS with pruning, which may increase the likelihood of errors during development. After evaluating these options, the DFS with pruning strategy emerges as the most practical choice. It strikes a balance between simplicity, efficiency, and ease of implementation. Brute force is clearly infeasible for larger graphs due to its exponential growth, and while dynamic programming is theoretically optimal, its memory overhead makes it less attractive in practice. The DFS-based solution takes advantage of the graph structure and adheres to the problem's constraints effectively, making it the best overall approach. Every approach comes with trade-offs. The DFS with pruning method is intuitive to implement and efficient for most use cases. though it may still explore some suboptimal paths that a DP approach would avoid. On the other hand, dynamic programming guarantees optimality but at the cost of high memory usage and increased implementation complexity. Brute force, while the simplest to implement, is computationally impractical for all but the smallest graphs. Ultimately, DFS with pruning achieves a balance between performance and simplicity, making it the ideal choice for solving this problem. By leveraging key observations, such as allowing revisits to nodes, pruning based on the time constraint, and using memoization to avoid redundant calculations, this approach efficiently narrows the search space while satisfying the problem's constraints. To solve the problem of maximizing the path quality in a graph, we start by representing the graph in a format that's efficient for traversal. An adjacency list is ideal for this purpose because it allows us to quickly access the neighbors of each node. For example, given edges with weights, we can construct a dictionary where each node points to a list of its neighbors along with the travel times to those neighbors. Additionally, the values associated with each node are stored in an array for quick access. This setup provides all the foundational data we need to efficiently explore the graph and calculate path quality. Now, the problem imposes certain constraints and objectives that guide our approach. First, we always begin traversing from node 0. The total time spent on any path must not exceed the given max time, which ensures that only feasible paths are considered. While nodes can be revisited, the value of a node is added to the path quality only the first time it's visited. Our main objective is to maximize this path quality by carefully choosing which paths to explore under these constraints. To effectively navigate the graph and evaluate potential paths, we use depth-first search, or DFS, combined with backtracking. This method allows us to explore all possible paths systematically while undoing changes to try other alternatives, ensuring no possibilities are missed. The DFS algorithm starts at node 0, initializing the time spent in path quality with the value of the starting node. To track whether a node has been visited, we maintain a visited array. This ensures that the value of a node is added to the path quality only once. For each neighbor of the current node, we calculate the time required to reach that neighbor and check if it fits within the max time constraint. If it does, we proceed to visit the neighbor, updating the path quality if it's the first visit. After exploring a neighbor, we backtrack by reverting the changes to the visited array, allowing us to explore other paths independently. This systematic exploration ensures that we evaluate all valid paths while adhering to the constraints. To implement this approach, we initialize the visited array and a variable to track the maximum path quality found so far. The DFS begins at node 0, with the starting time and path quality set to the value of node 0. Key operations like tracking visits help avoid redundant calculations, ensuring node values are added to the quality only once per path. Additionally, we prune paths by stopping exploration as soon as the max time constraint is violated, which avoids unnecessary computations. By leveraging data structures like the adjacency list and the values array, we can access required information efficiently. Overall, this problem can be seen as a constrained graph traversal where backtracking is essential for exploring alternative paths. The time complexity is determined by the need to explore all subsets of nodes in the graph, while the space complexity accounts for the visited array and the recursion stack. Here, we start by importing the necessary libraries and defining the class solution, which contains our main function maximal path quality. The goal of this function is to calculate the maximum path quality in the graph based on the given constraints. We begin by constructing the graph as an adjacency list using the default dict from the collections module. Each node is connected to its neighbors along with the travel time between them. Next, we define the variable max_quality to keep track of the highest path quality found so far, and n to store the number of nodes in the graph. To explore the graph, we implement a depth-first search, or DFS, which is defined as an inner function. This function takes several parameters: the current node, the time used so far, the accumulated path quality, and a list to track how many times each node has been visited. When visiting a node for the first time, we add its value to the path quality. If the current node is the starting node, which is node 0, we check if the current path quality is greater than the maximum found so far and update max_quality accordingly. To ensure we don't double count values, we mark the current node as visited. Once the current node is marked as visited, the algorithm explores all its neighbors. For each neighbor, it checks whether the total travel time, including the time to reach the neighbor, stays within the allowed max time. If it does, the DFS function is called recursively to continue exploring from that neighbor. This ensures that all valid paths are considered. After exploring all neighbors, the algorithm backtracks by unmarking the current node, allowing it to be revisited in other potential paths. Finally, we initialize the visited list with zeros, indicating that no nodes have been visited yet, and start the DFS from node 0 with an initial time of 0 and a path quality of 0. The function ultimately returns the maximum path quality found. This approach ensures we explore all possible paths within the given constraints and calculate the optimal path quality efficiently. Here, we begin by defining the maximal path quality method, which takes 3 parameters, an array values representing the quality of each node, a 2D array edges representing the graph's connections and their respective travel times, and max time, the maximum allowed travel time for the path. First, we build the graph as an adjacency list using a hash map. Each node maps to a list of its neighbors, or each neighbor is represented as an array containing the destination node and the travel time. This structure allows efficient traversal of the graph. Next, we initialize some variables. N stores the number of nodes in the graph, and max quality is an array of size 1 to store the maximum path quality as we explore. The visited array tracks how many times we've visited each node. To explore the graph and calculate path quality, we use a depth-first search (DFS) approach implemented in the DFS method. We start the DFS from node 0, with an initial time and path quality of 0. Inside the DFS method, we increment the path quality only if we're visiting the node for the first time, as indicated by the visited array. If the current node is the start node, which is node 0, we check if the current path quality is greater than the maximum path quality we've encountered so far. If it is, we update max quality accordingly. This ensures that we always retain the highest path quality achieved during valid paths. We then mark the current node as visited by incrementing its count in the visited array. From here, we explore all neighbors of the current node. If the graph contains neighbors for this node, we iterate through each neighbor. For each neighbor, we extract the next node and the travel time to reach it. Before moving to the next node, we ensure that the total time used, including the travel time, does not exceed the allowed max time. If this condition is satisfied, we perform a recursive DFS call to continue exploring from the next node. Finally, we backtrack by decrementing the visit count for the current node. This step is crucial for ensuring that other paths in the DFS can explore the node without interference from the current path. This combination of recursion and backtracking allows us to explore all possible paths and calculate the maximum path quality efficiently. In this example, we're given a graph with 3 nodes and edges connecting them with specific travel times. The goal is to find the maximum path quality we can achieve within a time limit of 20. First, we represent the graph using an adjacency list. Each node is a key, and its value is a list of tuples, where each tuple represents a neighboring node and the travel time to it. Next, we initialize 2 variables, max_quality, which tracks the highest path quality found so far, and visited, which keeps track of how many times each node has been visited during our traversal. We then start a depth-first search (DFS) traversal from node 0. Initially, the time used is 0, and the path quality is 0. Upon visiting node 0 for the first time, we add its value to the path quality, resulting in a path quality of 5. Since we are back at the start node, max_quality is updated to reflect the current path quality of 5. From node 0, we explore its neighbors. First, we travel to node 1. The travel time is 5, so the total time used becomes 5. Since we are visiting node 1 for the first time, we add its value to the path quality, which now becomes 15. From node 1, we further explore its neighbor, node 2. Traveling to node 2 takes an additional 10 units of time, bringing the total time used to 15. After adding the value of node 2, the path quality becomes 30. From here, we backtrack to node 1, and then back to node 0, to explore other paths. Next, instead of visiting node 1, we travel directly to node 2 from node 0. This travel takes 15 units of time, so the total time used is now 15. Adding the value of node 2 gives a path quality of 20. Once again, we return to node 0. After exploring all possible paths within the time limit, the maximum path quality achieved is 30. Now let's look at another example, where the graph has a tighter time constraint. The graph consists of 4 nodes, and the edges define the travel times between them. The time limit for this example is only 10 units. We start by constructing the graph as an adjacency list, where each node is connected to its neighbors along with the respective travel times. Then, we begin a DFS traversal from node 0. Initially, the time used is 0, and the path quality is 0. Visiting node 0 adds its value to the path quality, so the path quality becomes 1. From node 0, we first explore its neighbor, node 1. Traveling to node 1 takes 4 units of time, so the total time used is now 4. Adding the value of node 1 increases the path quality to 3. From node 1, we proceed to its neighbor, node 2. This travel takes an additional 6 units of time, reaching the exact time limit of 10. Visiting node 2 adds its value to the path quality, which now becomes 6. After this, we backtrack to node 0 to explore other possibilities. Instead of node 1, we can travel directly from node 0 to node 3. This travel takes exactly 10 units of time, which is the limit. Adding the value of node 3 to the path quality gives a total path quality of 5. After considering all valid paths within the time limit, the maximum path quality achieved in this example is 6. In the final example, we have a graph with 3 nodes and edges connecting them, but the time limit is extremely restrictive, only 5 units. After constructing the adjacency list for the graph, we start the DFS traversal from node 0. Initially, the time used is 0, and the path quality is 0. Visiting node 0 adds its value to the path quality, making it 10. However, none of node 0's neighbors can be reached within the given time limit of 5. As a result, no further traversal is possible, and the final maximum path quality remains 10, which is simply the value of the starting node. To analyze the time complexity of our solution, we start with the depth-first search, or DFS, traversal of the graph. First, constructing the graph into an adjacency list from the input edges takes E time, where E represents the number of edges. This is straightforward as we simply loop through the edges and populate the list. Next, the DFS itself comes into play. Here, we explore all possible paths starting from node 0. Since cycles are allowed and nodes can be revisited, the DFS may visit each node multiple times. For each node, it iterates over its neighbors, and across all nodes, this results in a total of E neighbor iterations, given that the graph has V nodes and E edges. Now, the total number of recursive calls depends on the number of valid paths within the max time constraint. Let's denote this number of valid paths as P. Each path contributes to a recursive DFS call. Therefore, the overall time complexity of the DFS is P*E. In the worst-case scenario, if the graph is fully connected and the max time allows the exploration of all possible paths, the number of paths P can grow exponentially with the depth of recursion. This would lead to a worst-case time complexity of E*2 to the power of V. Now let's understand the space complexity of the solution. First, storing the graph as an adjacency list requires V plus E space, where V is the number of nodes and E is the number of edges. This is because we need space for all vertices and their corresponding edges. Then, we have the visited array, which keeps track of whether a node has been visited during the DFS. This array has a size of V, since there is one entry for each node. Additionally, the recursive DFS calls require space in the call stack. The depth of this recursion is determined by the length of the longest path in the graph. In the worst case, this depth can go up to the number of nodes, requiring V space on the recursion stack. When we combine these factors, the total auxiliary space complexity amounts to V plus E. When comparing this approach to a brute force solution, the advantages of the optimized DFS become clear. A naive brute force method would involve generating all possible paths in the graph and verifying if each one satisfies the max time constraint. This would result in an exponential time complexity of V, which is far worse than the DFS approach. The DFS-based solution, on the other hand, incorporates pruning techniques that prevent unnecessary path exploration. Although its worst-case time complexity is still exponential, E*2 to the power of V, the pruning ensures that many redundant branches of the recursion tree are avoided, making it far more practical. In conclusion, the time complexity in the worst case remains O(e*2 to the power of e, and the space complexity is O(v plus e), which is dominated by the graph storage and the recursion stack. While exponential in the worst case, the pruning and early termination mechanisms make the DFS approach significantly more efficient than brute force in real-world scenarios. When working on this problem, there are several common mistakes to watch out for. First, ignoring the time constraint is a frequent issue. Some solutions focus solely on maximizing path quality without checking if the time limit is exceeded, which leads to invalid paths. Always ensure you're validating the cumulative time at every step of your traversal. Next, revisiting nodes without proper deduplication can also cause problems. If you aren't careful, you might accidentally overcount or undercount the path quality when nodes are revisited. Make sure you handle these revisit scenarios properly and calculate path quality only when the constraints are satisfied. Another pitfall is infinite loops during graph traversal. This often happens in DFS or backtracking approaches when stopping conditions or base cases are missing. To avoid this, include proper checks to terminate the traversal when constraints are violated. For larger graphs, brute force methods can quickly become inefficient. If the graph has a high number of nodes, like 10,000 or more, you'll need to optimize using techniques like memoization or priority queues to reduce redundant computations. Finally, failing to handle edge cases is another trap. Disconnected graphs, single-node graphs, or scenarios where the start and end nodes are the same should all be carefully tested to ensure your solution is robust and error-free. Now, let's talk about some useful insights for interviews. One area interviewers often focus on is how well you understand and handle constraints, such as time limits or rules for revisiting nodes. Be prepared to explain how your solution respects these constraints. Another key point is knowing when to use DFS versus BFS. DFS is great for exhaustive searches when backtracking is needed, while BFS is better suited for scenarios similar to shortest path problems. Make sure you can articulate why your chosen approach is optimal for the problem. Also, optimization techniques are frequently discussed. You should be ready to explain how you'd handle larger inputs, such as by using pruning to eliminate unviable paths, memoization to avoid redundant computations, or dynamic programming for state management. Lastly, debugging strategies are often part of the conversation. Be prepared to describe how you'd address common issues like infinite loops in graph traversal or mistakes in calculating path quality. This demonstrates your ability to troubleshoot and refine your solution effectively. There are also related problems and alternative approaches that can deepen your understanding of graph traversal under constraints. For instance, LeetCode number 847, shortest path visiting all nodes, involves visiting nodes with constraints, making it highly relevant. Similarly, LeetCode number 743, network delay time, focuses on finding the shortest path while adhering to time constraints. LeetCode number 980, unique paths 3, introduces constraints on how nodes are visited, and LeetCode number 1293, shortest path in a grid with obstacles elimination, combines graph traversal with specific constraints and optimization requirements. Considering alternative approaches, DFS with pruning is a common method. It allows you to backtrack when constraints are violated, making it intuitive, though it may be slow for larger graphs. BFS with state tracking is another option and is often more efficient for finding the optimal solution. However, it requires careful management of the state, including the current node, time spent, and path quality. Lastly, dynamic programming can be helpful, as it uses a table to store the maximum path quality for each node and time combination. This reduces redundant computations but comes with higher memory usage. Each of these approaches has its strengths and trade-offs, so understanding when to apply them is valuable. Finally, let's consider the trade-offs between the different approaches. DFS is well suited for exhaustive searches, as it explores deeper paths first, while BFS is better for scenarios where shorter paths need to be explored sooner, often resulting in faster solutions for optimization problems. However, BFS and dynamic programming typically require more memory compared to recursive DFS, which relies on the call stack. Space complexity is an important consideration, especially when working with large graphs. Runtime optimization is another critical factor. Regardless of the approach, pruning unviable paths early, such as those that exceed the time limit, can significantly improve efficiency. For larger inputs, this kind of optimization is essential to ensure your solution runs within a reasonable timeframe. Balancing these trade-offs will help you choose the most appropriate method for solving the problem effectively. Great job! We've successfully solved LeetCode number 2065, maximum path quality of a graph. Remember, backtracking and constraint handling are valuable skills for similar problems. Thank you for tuning in, and don't forget to like and subscribe for more insights and strategies. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!